Okay, let's get back to it now with problem 4.3 from Wald's general relativity, where in part A here he wants us to derive equation 4.4.24, which I have kind of at the bottom here, this acceleration equation that looks like an electromagnetism thing. So we're essentially deriving gravido-electromagnetism here. I found this problem to be pretty challenging as well, so I just put the name of someone from Stack Exchange whose solution really helped me get through this. It's Indicative Indigo, so shout out to them, thanks. I'm basically using your solution here. And yeah, let's get started. So for part A, let's start by writing down our assumptions. So we're still looking at linearized gravity. The main difference from what's done in the text here is that we're considering the lowest order contributions from the motion of the sources. So we can still assume that the metric GAB is the flat metric eta AB plus a perturbation gamma AB, where gamma is small. And with this, we know that GAB upstairs is simply eta AB minus gamma AB, like this. And so the way we're going to do this problem is we're going to only keep terms linear in gamma. So this is a consequence. Say thus, the covariant derivative of gamma is simply the ordinary derivative of gamma, since the Christoffel terms would be of order at least gamma squared. So throughout the problem, we make this assumption. And now I'm just going to write down the equation for the Christoffel symbols. This is going to be straight from Wald here. So 1/2 GCD del A GBD plus del B GAD. No, that's a minus del D GAB. Oops. Now, remember we're going to swap our metric out with the flat spacetime metric plus a perturbation, and we know the derivative of the flat spacetime metric already is just 0. So we can rewrite this off the bat like this. So let's sub in for this one, eta CD upstairs minus gamma CD upstairs. But inside, these are just going to be gammas when the derivatives are taken. Oops. Like this. So this is already simplified quite considerably, but you'll notice that the second term, as it multiplies in, these are all going to be second order in gamma, so we can effectively just get rid of that term. So I could rewrite this again with the eta out front, but let's just use it to raise indices here to clean up even further. So we'll go ahead and do that, and we get a del, I can't write today, del A, gamma B, and then the D comes up and becomes a C. We get del B, gamma A, the D comes up and becomes a C again, and then minus del C upstairs, gamma AB. So this is our Christoffel symbol equation that we can come back to later. Okay, now we can consider the geodesic equation for a test particle moving in the spacetime. So from the geodesic equation, we can write down something like this, where x mu is just the particle's world line, and tau is going to be an affine parameter of some kind. So that's our geodesic equation, and we can now rewrite this because we know the second derivative of a particle's world line with respect to an affine parameter is just going to be an acceleration of some sort. So let's write this as a mu plus, we'll keep the Christoffel symbol here, but these, the first derivatives of the particle's world line with respect to the affine parameter, are just going to be velocities. So we'll call this v rho v sigma equals 0. We're assuming that the spatial velocity is much less than c. So we can kind of think of these v's as having a number close to 1 as their 0th index, and very small numbers as their spatial indices, or their spatial slots, whatever you want to call it, such that if we had like v1 times v1, that would be small enough to discard. So that's how we're going to treat this here. So let's rewrite it just to solve for a mu. So it's simple. It's just minus mu rho sigma v rho v sigma. And then we can make use of the fact that we know that these velocities are small in the spatial directions. So with this, we can write, there's going to be a term where both of these get their 0 index, so they're both close to 1. So the term is just going to look effectively like that. And then we're going to have a term, let's see, like this, where we're keeping one of these i's spatial components, and then the other one is the time component, which is close to 1, so we just put it in as a 1. And then we do the same thing when the other v takes on a spatial component. So it looks like this. And then there's, I mean, technically another term here that's of order vi squared. Now we can make use of the symmetry of the Christoffel symbols. Since we know they're symmetric in the lower indices, we can collect these two terms together. We get a mu is minus gamma 0, 0 mu minus 2 gamma 0I mu vi, like this. So we can also just save this equation for later. Okay. So now for convenience, we can define some quantities. So we're going to define gamma bar AB, just to simplify the calculations, is gamma AB, and this is what they do in the book too, we're just kind of following their formalism, minus eta AB times gamma, where gamma is just this. So this is one equation we're going to want to hold on to. We can also take the trace of this equation, so bringing the b up and making it an a, and we find that gamma bar is just gamma minus delta AA gamma. So this delta AA is going to give a 4. Oh, there should have been a half here though, sorry. 1/2. So what this ends up telling us is that gamma bar is minus gamma. Then we can also go ahead and kind of like invert this one using these facts. So we can say that gamma bar AB, and then let's take the eta term over to this side. 1/2 eta AB, and then this is going to be a gamma, but we know that gamma is just minus gamma bar, and this is going to be set equal to gamma AB. So let's flip it around now because we're looking for an equation on gamma AB. Equals gamma bar AB minus 1/2 eta AB gamma bar. So just kind of like a backwards version of the equation we first wrote down. Okay, and we're in a spot now to kind of start solving the problem. So let's use an equation from Wald. this is going to be equation 4.4.12. This tells us that del C on gamma bar AB is minus 16 pi times the stress energy tensor. And just like in the book, we let TAB be 2 TAJB minus rho TATB, where T is the forward velocity of the source. So basically, in the way they do it in the book, they assume that T is just 1, 0, 0, 0. But in this formulation of the problem, we're assuming that T can have components besides in the time direction. And so that's what's going to give us different results. So this is, let's see, the symmetric part of TAB, and this one is going to be in the 0, 0 slot only, because we have two TABs here, or it's two TAs, TA times TB, however you want to say that. So it's going to be small enough in the non-time slot that when it is multiplied by itself like that, it would go away if it weren't just the time slots. Okay, so with this we can carry on here, and so since JB has a TA in it, it's only non-zero if either A or B are 0, but not at the same time because of symmetry reasons. So we can write down the energy momentum tensor like this, where these Y's are mass current densities or momentum densities. And we can populate the rest of the tensor with zeros. So we don't actually really need to write this down, but this kind of just helps to think about the problem, because now we can start working out this equation that we have in the box and thinking about the different cases for it. So time happens to be the same as before when they did it in the book, without taking into account the lowest order contributions of the motion of the source. So this equation just looks like del squared gamma bar 0, 0 equals minus 16 pi rho. So it's unchanged. Space is also unchanged. Del squared gamma bar AB equals 0. But the time space equations are the ones that are different now because of these J's. So we get a del C, del C gamma bar 0 I is 16 pi JI, where, I mean, you can think of these JIs as momentum densities, so you can write this as rho times the velocities Vy, Vx, Vz. Or similarly, this could be rho just times a vector V, we'll call it Vi. So just a momentum density. Okay, so the equation that we're mostly interested in here is up here, and what I want to do now is draw a comparison between this equation and one of Maxwell's equations. If I can get this box right. Thank you. Okay. So let's write down one of Maxwell's equations directly here. We have del C, and then the vector potential AB here, and this is going to be minus 4 pi JB. So this again is directly from Maxwell, and we want to draw an analogy between these two equations. So in order to do this, we're going to define a vector potential of our own. So let's do that. So we can define it in terms of gamma bar with the TV here. And remember, we're considering small velocities for the source, so we have that TV is basically this. So with these facts, we can multiply both sides by a TC. But these together are going to give -1 if C is equal to B and 0 otherwise. So in other words, that's a minus delta CB basically. So we get that AATC is -1/4 gamma bar AC. And sorry, this shouldn't be a minus anymore. This is going to be a plus from the minus sign here. Now, if we, let's see what we can do. If we raise a C and make it into an A on both sides, end up with something like this. We'd use the metric to do that, but I'm just going to kind of skip that step, and we get a gamma bar here. We get an AA. Now, let's think about, actually, we don't have to think about this just yet. Let's just say that this means we get an A0 on the left side, and that we can take the 4 over, so we get 4A0 is gamma bar. Okay, let's see, from this equation, from this equation we can see that gamma bar 0, 0 is simply -4A0 and yeah, to make like Maxwell, the last thing we're going to do we're going to let our A look like this, phi, and then an A mu with 3 indices in the second one. Actually, let's do it this way. A mu equals minus phi AI. I like that better. Okay. So this stuff is going to come in handy later, or especially when we compute the Christoffel symbols and we get derivatives of these gamma terms. And we can go ahead and get started with computing the Christoffel symbols right now using just the normal equation from Wald. But we don't need to calculate all of them, so let's go back and look at our acceleration equation we've already derived. And we'll notice we need one with an arbitrary top index but zeros on the bottom, and one with an arbitrary top index but 0i on the bottom. So that isn't too hard. We can go ahead and compute those directly here. So let's use the equation on the right, remembering that for us, G mu nu is eta mu nu plus gamma mu nu. So we can simplify this a lot right off the bat. So gamma 0, 0i is going to be 1/2 G I, actually, we already know that this can just be written as an eta because the gammas will multiply by the gammas from the G's here and give us second order terms, so we could just skip that. So instead we have eta I sigma del 0 of, we'll just write the gammas because the derivatives of the etas are going to be 0 as well. And this is going to be 0 sigma plus del 0 gamma 0 sigma again minus del sigma gamma 0 0. So it says in the text that we're under the quasi-static approximation, so these time derivatives of gamma can go to 0. We're assuming that it's not changing or changing very slowly. And then we can rewrite that this is simply 1/2. And let's use the eta to raise this sigma. So we get minus del I upstairs gamma 0 0. But we can recall from earlier that gamma 0 0 is simply going to be gamma bar 0 0 minus 1/2 eta 0 0 gamma bar. We know that eta 0 0 is simply 1, is simply minus 1. We also know that gamma bar 0 0 is going to be minus 4a naught. I think we wrote that down just up here. Yeah, gamma bar 0 0 is minus 4a naught. So then the minus sign from the eta is going to come up front here. We get a plus 1/2 gamma bar, but we also know gamma bar in terms of a naught. Gamma bar is just 4a naught. So we can also plug this in. And we end up with minus 2a naught. And if we look at a one more time, remember that a0 is simply minus phi. So we end up with 2 phi here for gamma 0 0. So more explicitly then for the Christoffel symbols, we'll just write thus gamma I 0 0 equals minus 1/2 del I times 2 phi, or this is minus del I phi. Okay, so we can try the next Christoffel symbol now. So again, we're under the quasi-static approximation, and this first term goes away, and we can use the etas to raise indices, or not the etas, but the 1 eta to raise indices here. So let's do that. We get del I gamma 0 mu minus del mu gamma 0 I. So we actually need to work out what these gamma 0 i's are going to be. So we can do that over here. Let's recall a few facts. Gamma bar is 4a naught. Gamma bar 0 0 is minus 4a naught. And AA is minus 1/4. Gamma bar AB TB. So this means then that A can be written minus 1/4 gamma bar A0. And so this means gamma bar, write it this way. 0I minus 4AI. Since these gammas are symmetric. Oh yeah, and then I guess we should also write it this way. It's gamma bar 0 with the I raised. It's going to be minus 4AI. So let's make use of that over here. Yeah, so with this we can say this equals 1/2 delta I minus 4A mu minus delta mu minus 4AI. So we can pull those minus 4s out, and we get a 2 up front. We get, let's take the positive term first. Actually, no, let's take the minus sign up front. We got delta I A mu minus delta mu AI. Or if we don't take the minus sign up front, I guess this is probably the better way to write it. Del mu AI minus del I A mu. So now we do a little bit of recollection from electromagnetism. So recall in E&M that the electromagnetic tensor Fij is this, del IAJ minus LJ AI. So that means that we have something like F mu I. This is going to be del mu AI minus del I A mu. So with this, we can kind of see the pattern over here and simply say that gamma mu 0I is 2 F mu I. Okay, so this is getting relatively close to the end of the problem now. Okay, so just some more definitions from E&M. Let's say we're going to define E to be this, the electric field to be minus del phi minus del TA, and the magnetic field. And you can just get this from any E&M textbook. Cos A. So if we write these in index notation instead, also making the assumption that del T, A is 0. We're assuming things are static with respect to time. Get EI equals minus del I phi, and BI equals epsilon I JK, or that's the Levi-Civita tensor, del J 8K. And similarly, we can write down the term B cross B, because we know that that has to show up in our final answer. So let's see what that's going to look like in index notation as well. So we can say V cross B I is epsilon I JK VJ BK. but we have a definition for B over here, so let's just go ahead and sub it in. So we get epsilon I j k Vj times bk. So here I'm going to put in an epsilon k l m delta l a m. Okay, so let's bring the Relativity tensors together. But we know, you can find this on Wikipedia or something similar, that epsilon ijk downstairs times epsilon pq k upstairs is going to be this combination of deltas. So let's manipulate the deltas, the Relativity tensors to get something like this. So we can leave this one alone, but let's try and get this k to the end of this one. So that'll be one permutation, which gives us the minus sign, but then one more permutation, which takes the minus sign away. And we end up with epsilon lmk Vj delta lam. So let's go ahead and put the deltas in that we get from these epsilons now. Delta L I delta M J minus delta M I delta L J times Vj del L AM. Okay, so we can just apply these deltas and get close to a final answer here. Get Vm del I AM, because the J goes to an M, the L goes to an I, and then the M stays the way it is. And then the second one we get VL del L AI. So finally, we can clean up a little bit. B cross, B I is simply pull out the VM delta I, or del I AM minus del M AI. Or if you like, remembering the definition of the electromagnetic tensor from above, you could do it this way as well. So we're essentially at the end of the problem now. We can just return to our acceleration formula that we derived way at the start. So this is AJ equals minus gamma 0, 0, j plus 2 gamma 0 I j vi. And we can just start subbing things in. So minus sign we get for this one, remember, is del I phi, or minus del I phi, obviously, plus 2. This gamma is just 2f ji, if you remember from that part, times the vi here. And what can we do now? HA is, oh, this should be a J. Now we know that this is nothing more than minus EJ from our definitions up here. And we know that this term is nothing other than V cross B J. So let's go ahead and rewrite this. I could say AJ is minus EJ minus 4 E cross B J, which is exactly what the problem asked for. Okay, now for part B. He wants us to show that the gravitational, electric, and magnetic fields E and B inside a spherical shell of mass m and radius r, slowly rotating with an angular velocity omega, are the values shown here. So we can do that, and this is essentially completely analogous to a problem from Griffiths, so we are going to follow the formalism of Griffiths to get there. Okay, so we know from part A, we know a few things. We know that del A gamma bar 0 mu is 16 pi j mu. So this means so just simplifying, taking the constants out, etc. So the reason I write this like this is because it's almost exactly analogous to Griffiths, what they do right here. It's essentially a collection of 3 Poisson's equations, and in Griffiths, when this is true, you can find the vector potential by doing this integral on J. So we're going to do that, but instead of mu naught, we're going to use 4 as our constant. Sorry, 4 pi. Forgot to write the pi. Okay. So I'm going to copy down that exact equation. So it's going to be c over 4 pi integral j mu for r over the area element. So Griffiths tells us what script r is, so we can go ahead with that. We also know that c is 4 pi, so we're just going to get rid of this term in front altogether. So we'll just write down that r is square root of r squared plus r squared minus 2rr cos theta. And remember that the area element is going to be r squared, because this is a spherical shell, sine theta d theta d phi. So right off the bat, we don't even have to do any work. We can just say by Gauss's law, E equals 0 inside the shell. Because you would not enclose any charge or any mass in this case. And recall what we said in the last problem, that J mu is effectively just rho times these velocities. But the velocity of the shell is just going to be this expression here. So remember, v equals omega cross r. So we can rewrite J mu. So we can rewrite J mu by using what Griffiths gets for omega cross r here. I mean, you can do the work and show this, but we're just going to take it. So we see we get an r and omega out here from the v cross r. we're going to have a row, and then we get these components. So let's write it out as a vector. So we keep our row, and then we get our omega from the cross product, and then we get this vector. So we get minus cos phi sine theta sine phi. The first one I should have said psi, and I haven't introduced what psi is yet. So what they do actually, they say it might seem natural to set the polar axis along omega, the angular velocity, but in fact the integration is easier if we let r lie on the z-axis. So this psi is the angle between the z-axis and omega, the angular velocity. So that's the first component of this vector. We get a cos psi sine theta cos phi minus sine psi cos theta, and a sine psi in the z component, sine theta, sine phi. And so the argument that Griffiths makes here is that we're integrating this j, and so they say that terms involving sine of phi and cos of phi go to 0, since let me just check which angle phi is. Phi is going from 0 to 2 pi. So it's just because of the symmetry of the functions, essentially. These integrals are going to evaluate to 0. So with that, there's a bunch of terms we can set to 0, and the only term that actually survives is this one here, the minus sine psi cos theta after integration. So we're going to just call this j prime mu. It's like an effective j that we can use for the integration. Okay, so this is what we're going to integrate, and we can go ahead and set this up now. So we can do the integral, well, we know a0 and a2 are going to evaluate to 0, but we can write down an equation for a1. So this integral, we're going to get rho r omega minus sine psi cos theta times the area element here, r squared sine theta d theta d phi. This is going to be divided by that script r that we had. So let's see, d theta is going to go from 0 to pi, and phi is going to go from 0 to 2 pi. So now we can pull out things that are going to be constant, which is a lot. We get minus rho r cubed omega sine psi times the integral from 0 to pi of, actually there's going to be also a 2 pi out front here, so let's put the minus here and say 2 pi cos theta over the square root that I'm not going to write again, d theta. The 2 pi just comes from the integral of d phi. Now for evaluating this integral, we can look to Griffiths. So the messy integral expression reduces to inside the sphere 2r over 3r squared. So we can use that as our integral. Can write it here. Times minus 2 pi rho r cubed omega sine psi. But this is right from Griffiths. We can say that that minus omega r sine psi is omega cross r. So we're going to make use of that fact because they do it. So we do 2r over 3r squared. This is our a1, by the way. And then, so we'll get rid of the minus sign, the w, oh, I guess the r. So I'll erase that. And sine phi. Okay, so we're left with 2 pi rho r cubed, and then we get omega cross r. So we can cancel some things out. First, actually, let's say, remember that density is just mass over either volume or, in this case, surface area, because it's a spherical shell. So we get a 4 pi r squared in the denominator, and we can simplify this once more. So 2 over 3 r squared, and actually, let's get rid of the r squared here. Because of that, get 2 pi rho r omega cross r, and I forgot to get rid of the rho, so let's just erase it and write what it is. Mass over 4 pi r squared. So this r is going to cancel one of these, pi is going to cancel, 4 is going to cancel with both of these 2's, and we get m over 3 r times omega cross r. Now remember, we're still in those kind of weird coordinates where the angular velocity is not aligned with the z direction, so let's change back now, revert to the natural coordinates, and Griffiths tells us that we can do this way. So let's go ahead. So now we're going to be talking about a phi is m over 3r times omega r sine theta phi hat. And what do we know about b? We know that b is exactly this, the curl of A. And in spherical coordinates, that's going to look like this. You can get this right from Wikipedia or something like that if you don't want to drive it. Just look up the curl in spherical coordinates. You're going to have a del theta, a phi sine theta, r hat, minus 1 over r del r, r a phi, theta hat. So we can go ahead with that. Well, actually, we can pull out the constants. sine squared theta r squared sine theta in the theta hat direction. So we can take these derivatives now. This is going to be 2r sine theta cos theta in the r hat direction minus 1 over r 2r sine theta in the theta hat direction. So r cancels here, sine theta cancels here, r cancels here, and we get 2 cos theta r hat minus 2 sine theta theta hat. So if we factor out the 2, we'll realize that this here is nothing other than z hat. And also we can think about the fact that omega times z hat is just omega in our current coordinate system. So let's rewrite this again. For the electric field, for the magnetic field, which is exactly what the problem had asked us to show. Okay, and now finally we can have a look at part C. So part C says that an observer at rest at the center of the shell of part B parallelly propagates along his geodesic world line a vector SA, where SA UA is 0 and UA is the tangent to the world line. So you want to show that the inertial components S process according to this equation, where omega is 2b. And yeah, it talks a little bit about the history of the effect. So that's fine. Let's just go ahead and get right through this. Okay, so what do we have? We have that SAUA equals 0. So S is some vector parallelly propagated. And UA is a tangent to the geodesic. So parallel transport means this. So we can write the geodesic equation down. Get but in global inertial coordinates, what is it? U mu is basically this. So actually, we can just take this over to the other side and get rid of the u in the same step. It's going to have the effect of giving us gamma nu, fixing a 0 into this index, lambda s lambda. But remember in part A, we showed this relation for the Christoffel symbol. So let's just plug that in. But in part B, we actually showed that this is S cross B nu. So we can rewrite the derivative again as minus 2f nu lambda s lambda. Oh, I didn't need to rewrite that, sorry. Instead, we're going to rewrite it as minus 2 S cross B nu. But since 2b is omega, we get ds nu by dt is minus S cross omega nu, or if we reverse the order, the minus sign goes away and we get omega cross S nu as the problem asks us to show.